Hey Global Impact students, this is Mr. Ellinger. This lesson is on literal equations and formulas. Our learning target for the lesson is to rewrite and use literal equations and formulas. Essential understanding for the lesson: a literal equation is an equation that involves two or more variables. The solution to a literal equation can be found using the properties of equality and inverse operations to form a series of simpler equations. Also, the properties of equality can be used repeatedly to isolate any particular variable. When solving literal equations, all variables that are not being solved for can be treated as constants. Background for the lesson: this skill is particularly useful when working with formulas in science and mathematics classes. We've talked about what it means to solve an equation or an inequality. This lesson is going to put a different spin on the word solve. Conceptually, it's still the same. We know solve means to isolate a variable. But what we're going to be doing now is the other side of the equation is not going to be a number. In this lesson, we're still isolating a variable to solve an equation, but the other side will not be a single number. And this skill is helpful when we're using formulas. A lot of times we'll use formulas in science or math that are a little complex, and we'll want to be solving for a particular variable that's right in the middle of this complex formula, and sometimes it's easier to just rewrite the formula in terms of the variable that we're actually going to be solving for. It's also going to come in handy when we start working with functions. Functions will come in our next unit. I have two equations down here. 2x plus 3y equals 6 right here. That's a two-variable equation, so by the definition, this is what we call a literal equation. But what I can do with this equation is I can rewrite it so that y is by itself, y is solved. So down here I have y equals negative 2/3 x plus 2. These two equations look very different, but they're actually equivalent, or the same. They're just rewritten in a different form. If we take this equation and solve it for y, this is what we get. Okay, it's solved for y. Y is isolated. Now on the other side, we don't have just a plain old number. We have a variable x with a coefficient and another constant term, but this is still what we call solved. So let's take a look at how we do this. First example here, we have negative t equals r plus px. Now right away, you'll notice both of these examples do not have any numbers in them at all. And there's a tendency to kind of freak out a little bit when we don't see any numbers because we're so used to working with numbers. We're used to solving and getting numerical answers. We just have to try our best to get out of that mentality. What does it mean to solve for x? Well, here's x. X is on the right side of the equal sign. X has a coefficient of p. Now p is a letter, but it's still in the coefficient position, if you will. And remember, it said all the other variables that we're not solving for can be treated as constants. So we just need to look at this minus t and this r and this p as constants or numbers. We're going to solve this for x, which means we want to isolate x. So I know at some point I'm going to divide by p, but first I want to move the r to the other side of the equation. Why am I going to do that? Well, the r is positive here, so I'm going to subtract r from both sides. R minus r is a 0, so that leaves px on the right side. Negative t minus r. I can't calculate that. I have no idea what t and r are. I can't combine them into one because they're different letters, different variables, so all I can do is just write negative t minus r. The next step is to isolate x. Since p is being multiplied by x, we will divide both sides by p. P divided by p is 1. That gives us our x with a coefficient of 1. Now when we divide this side by p, we've got to divide this whole side by p. Not just one of these letters, but the whole thing. Negative t minus r all over p. Again, no numbers, so there's nothing we can calculate. So we will just write negative t minus r over p. That is solved for x. That's it. Right, our next equation, we want to solve for x. A little bit different here. We have x's on both sides of the equation. So we want to collect our x terms all on one side. So the first thing that we'll do is, let's bring this bx term over here with ax. On the right side of the equation, it's minus bx or negative bx, so let's add bx to both sides. This is 0 on the right side, that gives me a 0, so I'll bring my c down. Ax plus bx, well, let's just write ax plus bx for now, minus d. I want all my constants on the other side, so I'm going to add d to both sides. I'm trying to isolate x. So I have ax plus bx equals c plus d. Now at this point, when we get here, ax plus bx, we might get a little stuck because we might say, okay, I'm trying to isolate x, but right now I have two x terms. And I know that if these were numbers, like 2x and 3x, I could add those together to get 5x. Well, we can still do that. We know that when combining like terms, we take the coefficients and we add them together. So a plus b times x equals c plus d. A plus b is what I would do to add those two terms together, to combine them into one term. After I do that, I ran out of room here at the bottom, so let me just kind of transfer this over here. So there's the line that I had here. So now isolate x. A plus b is a quantity. It's one value, it's a quantity, so I can divide both sides by that a plus b. A plus b divided by a plus b gives me a 1, a coefficient of 1 on x, which is what I want. And here, no numbers, so I can't calculate anything. Without any numerical values, we can't do any calculations. So here, this is solved for x. X equals c plus d over a plus b. Clearly, this equation looks nothing like our starting equation, but those two equations are what we call equivalent. Okay, here are some common formulas that we use that you've probably used up until now. We have perimeter, circumference, some geometric formulas. We have a formula, distance traveled, very common formula in physical science. We use it periodically in math class as well. We have a temperature conversion equation, degrees Celsius equals 5/9 times the quantity F for Fahrenheit minus 32. One thing that we might want to be able to do is take our D equals RT. Say we were doing a word problem and we were asked to find a rate. Well, if we were asked to find a rate, we would know D and we would know T. So we would have to plug those values in to solve for R, and that's not that big of a deal. But it's helpful to understand that if I wanted R by itself, I would need to divide by T. So I could use this equation when solving for a rate. Similarly, I could use this equation when solving for a time, a period of time. If I know a distance and the rate traveled, I can do some division there to find the time traveled. So R equals D over T, T equals D over R are just different forms of this equation D equals RT. Now, let's say we were doing some temperature conversions. We didn't have a calculator handy, so we had to do it the old-fashioned way. And we knew some temperatures in Fahrenheit. We would just have to add 32, get that value, and then multiply it by 5/9 to get the Celsius equivalent. Well, if we knew the Celsius temperature and wanted to know the Fahrenheit temperature, the task of converting that would be a little more daunting. So what we can do is we can rewrite this solved for F. Now, since F is inside this parentheses, let's remember our trick that says we can divide the other side by this number to clear that number out of the parentheses. Now, since that is a fraction, what we could remember is that if I multiply this by its reciprocal, 9/5, I know it's kind of tight, 9/5 times 5/9 is a 1. So that would give me a 1 coefficient on this parentheses, which essentially allows me to drop the parentheses. But I also have to multiply this side by 9/5. So right now I have 9/5 C equals F plus 32. But I want F by itself, so all I'll do is just subtract 32 from both sides. And that'll give me 9/5 C minus 32 equals F. Let me write that over here so it's not so sloppy. This is how we would find a Fahrenheit temperature if we knew a Celsius temperature. a little bit easier to do this way than it would be to go back to our original equation, plug a value in for C, and try to solve for F. Okay, so here's another example. Pacific gray whales migrate annually from the waters near Alaska to the waters near Baja California, Mexico, and back. The whales travel a distance of about 5,000 miles each way at an average rate of 91 miles per day. How many days does it take the whales to migrate one way? So one way, they're going 5,000 miles. That's a distance. They tell us that they travel an average rate of 91 miles per day. What is that? Well, that is a rate. We'll talk about rates more here in a little bit. It's asking us about how many days. Well, that's our variable, t equals time. How are these all related? Well, we have a formula for that, right? Distance equals rate times time. In this case, we're asked to solve for a time, so we could rewrite this as d divided by r equals t. We know a distance is 5,000. We know our rate is 91. We just need to divide that to get t. I get a value of 54.945. The problem, again, anytime we're doing a word problem, we always want to go back to the problem that we're being asked. About how many days, so that's asking us for an approximation. About how many days does it take the whales to migrate one way? We got a value of 54.945. That's about 55. So we would say it takes about 55 days for the whales to migrate one way. This is the answer to the problem. This down here, if you stop there, it's going to be marked wrong. You did some math to help you solve the problem, but you did not solve the problem. You did not answer the question. So again, if you stop here, it will be marked incorrect. Carry out the rest of the problem, answer the question, write a sentence to address the problem. All right, I hope you guys have a great day.